Hello everyone and welcome back to Introduction to Number Theory. This time we will discuss the Chinese remainders theorem and proof of the existence of a solution by induction, and it could also be used as a method for solving such systems of congruences. Well, here we see a system of congruences, modular M1, M2, and so on Mk, and these moduli are pairwise mutually prime. So each two of them have no common divisor greater than 1. A1, A2, and so on Ak are just arbitrary integer numbers, and x is the unknown. We wish to prove that such a system of congruences has a solution, and this solution is unique, modular M1 multiplied by M2 multiplied by M3 and so on multiplied by Mk. In order to do this, let's take just two congruences, the first two, and show that the system of these two congruences is equivalent to one congruence of the form x congruent to, well, something. We can denote this something as a capital A or in some other way. It really doesn't matter how we denote it. What matters is that x will be equivalent to A, x will be congruent to A modular M1, M2. So we need to show that we can replace two congruences by one congruence modular the product of these two moduli. This will allow us to shorten the list of the congruences. If we have initially k congruences, then replacing two of them by one, we'll have k minus 1 congruences, and then take some other pair of congruences and replace it by one using the same method, the same idea. And eventually we will come up with one congruence of the form x congruent to, well, something, I don't know, alpha modular M1 multiplied by M2 multiplied by and so on multiplied by Mk, and this will finish the proof that the system of congruences has a solution, and the solution is unique modular the product of all these moduli. So now we need to prove that this pair of congruences is equivalent to one congruence of this form. Okay, well, write these congruences in another way. X is congruent to A1 modular M1. This means that x is equal to A1 plus M1 multiplied by some t, where t is an integer. It's just another way to write this congruence. So any x that is congruent to A1 modular M1 can be represented in this form, and any x represented in this form is congruent to A1 modular M1. At the same time, x is equal to A2 plus M2 multiplied by s, where s is an integer. So let me remind you that this is something like an equation, a system of equations. And here, if x is an unknown, then t is unknown and also s is unknown. Now we can exclude x from these two equations and write an equation on t and s, namely A1 plus M1t should be equal to A2 plus M 2s. Well, this is a linear Diophantine equation with two variables. We know how to solve such equations. Let's write it in standard form. m1 multiplied by t minus m2 multiplied by s is equal to a2 minus a1. Well, since m1 and m2 are mutually prime, this equation has a solution. The solution of this equation is given by formula t equal to t1, particular solution, plus m2l, and s equal to s1 plus m1l, where l is just an arbitrary, and this is important, arbitrary integer. So we can use any of these in order to express x from the initial system. Let's take t, formula for t, and eventually x is equal to a1 plus m1t, and we take t from here, so t1 plus m2l. After transformations, after some simple transformations, we obtain a1 plus m1t1 plus m1 m2l. And let me just remind you that t1 was just a particular solution of an equation. It's just a number. It is a constant number. It is a particular number. Also, m1 and a1 are fixed integers, whereas l is an arbitrary integer. So since t is expressed in this way with arbitrary l, then x is expressed in this way also with arbitrary l, which brings us to a conclusion that simply x must be congruent to a1 plus m1 t1 modulo m1 multiplied by m2. And this is the congruence we want to reach, because indeed x is congruent to something. It doesn't matter what it is written here. What matters is that it is congruent modulo m1 multiplied by m2. So this way we can replace pairs of congruences by one congruence until we reach only one congruence, and this will eventually prove the Chinese remainders theorem.